Greetings everyone, and welcome to a brief overview of projectile motion, Worksheet 5. A ball is launched from the ground with a velocity of 58.8 meters per second at 30 degrees. So this is our first problem where we are using a two-dimensional projectile motion with a ball launched at an angle. Since it's launched at an angle, that means that initially it is both moving horizontally and vertically. And so we need to figure out how much horizontally is it moving and how fast vertically is it moving. Since after all, our tact is always to take the two-dimensional motion and break it up into two one-dimensional motions. So to do that, we are going to draw ourselves a vector diagram and then apply some trig. So there's our initial velocity, technically 58.8 meters per second at 30 degrees. We can then break it down into the x component of the velocity and the y component of the initial velocity. Now, you may be saying to yourself, why did you write VOY here and VX here? Well, I could have really written VOX as well. I could have written it as the initial horizontal velocity. But what's special about the horizontal velocity of a projectile? That's right, it's constant. So the initial horizontal and the final horizontal are really all the same, so it really doesn't matter. The vertical, however, will change, as we will talk more about in a little bit. And there's the angle theta. So if we want to find Vx, it's the adjacent side to the angle, so we can use the cosine. We can say hypotenuse times the cosine of the angle, or VO cosine theta, is Vx. Plug in our numbers. We get 50.9 meters per second, or roughly 51 meters per second. That means every second it goes about 51 meters horizontally. Right? It's constant velocity, so it's really no more complex than that. Vertically, our initial vertical velocity would be VO sine theta, because VOY is, of course, the opposite side to the angle, so that's the hypotenuse times the sine of the angle. Plug in our numbers. Sine of 30 is, of course, 0.5, and we get 29.4 meters per second. Now again, this is only the initial vertical velocity. This is going to change. Horizontal velocity is constant, vertical velocity accelerates. Now let's fill in our table here. First of all, our general terms. We're not sure what the time is. Actually, if you look further down, we're going to plug in times of 1, 2, 3, 4, 5, 6 seconds. Our initial velocity is, of course, 58.8 meters per second, and our angle is 30 degrees. Horizontally, our initial position, since we're just launching from the ground and we don't have any other coordinate system, let's just say our initial position is 0 horizontally, just to make life easy. Our final position will depend on how much time has elapsed, so we're not really sure what that is. Our constant horizontal velocity, we just calculated, 50.9 meters per second, and our horizontal acceleration is important here. There are no horizontal forces acting on the projectile after it leaves, right? After it's launched. Only gravity acts. That's by definition projectile motion. Since there are no horizontal forces, there's no horizontal net force, which means no horizontal acceleration, which means the velocity is constant horizontally. Vertically, our initial vertical position, or our initial height, is the ground, which we'd probably call 0 meters. Our final height, we're not sure of. That'll depend on how much time elapses. Our final vertical velocity, we're not sure of. That would be how fast we're going after 1, 2, 3, 4, 5 seconds. We certainly could calculate it using one of the kinematic equations, but we don't need to here, right, unless it's asked for. Our initial vertical velocity, we just calculated a moment ago, 29.4 meters per second. And our vertical acceleration, well, since gravity is the only thing that's acting, gravity will result in an acceleration due to gravity of our old friend, negative 9.8 meters per second squared. That means on the way up, the ball will slow down 9.8 meters per second every second, and on the way down, it will speed up 9.8 meters per second every second. It's a uniformly accelerated motion. Now let's figure out where this ball will be horizontally and vertically at 3 seconds, and then you can just change the times to calculate any of the other times needed for the chart. So let's start out with the horizontal final position. Remember that our horizontal velocity is constant. So we only have one constant velocity equation, that's the range equation. It says horizontal displacement is horizontal velocity times time. This is just distance or displacement is velocity times time. Constant velocity, it's all you got to use. No kinematic equations needed here. We decided our initial horizontal position was 0, so plug in our horizontal velocity. Now, symbolically, it would be VO cosine theta. See the previous discussion. We could just plug in our number though, 50.9 meters per second at 3 seconds would be roughly 153 meters. Notice that's 51 meters every second, right? So 153 after 3. You may not even need to write this equation out if you understand what the constant horizontal velocity actually means. On the other hand, the vertical velocity, or position, is a little harder to do without using a kinematic equation. Now it is uniformly accelerated motion, so we can choose any of the appropriate kinematic equations to use here. I would choose equation number 3 because it fits. We know that the initial vertical position is 0. Right? We know that the initial vertical velocity is VO cosine theta, if you want to be generic. Right? Or it's 29.4 meters per second. Our g, our vertical acceleration, is negative 9.8 meters per second squared, and our time is 3 seconds. Don't lose the squared on this one. And you can't lose the negative sign here as well because you need to subtract this off. Otherwise, the thing will just keep going up higher and higher and higher, and that's not going to happen. So if you calculate that out, you get 44.1 meters. So this is the vertical position at 3 seconds. Plug in different times, and you can fill in the chart. It should look like this. Notice that the horizontal position increases constantly because it's a constant horizontal velocity, but the vertical position goes up and then comes back down because it's uniformly accelerated negative 9.8 meters per second squared. Let's graph the points. 0, 0, 51, 24.5, 102, 39.2, 153 and 44.1, 204 and 39.2, 255 and 24.5, and 306 and 0. So the shape of our path is in fact a parabola. Constant velocity horizontally, uniformly accelerated motion vertically makes a parabolic motion. Notice this isn't a time graph. This is a vertical position or height versus horizontal position graph. This is the actual positions of the ball every second. It's like a motion map that we're drawing out here, except we're actually drawing it to scale, if you will. Notice that I chose the numbers so that the 3 second was the highest point. And then we get this beautiful symmetry on either side of the highest point. Right? We get the equal but opposite parabola over there, which is going to kind of come in handy when we're trying to analyze what's going on. Now, not all parabolas would work this way. If we shot it off the table onto the floor, right, then we wouldn't get this nice symmetric shape the whole way. But in this case, I tried to keep things a little more straightforward so we can use symmetry. Now, I want to add some velocity arrows onto this to turn it into a little bit more of a motion map. But since it's two-dimensional motion, rather than drawing a single velocity arrow at some angle, I'm going to draw one for the horizontal velocity and one for the vertical velocity. So initially, this is after it's launched, just after it's launched, it has a horizontal velocity of roughly 51 meters every second. 1 second later, it still has a horizontal velocity of 51 meters per second. That's what it means to move at a constant velocity. So the same after 2 seconds, same at 3 seconds, 4 seconds, 5 seconds, and 6 seconds. Notice the horizontal velocities are constant. Do you see how each dot is the same distance to the right every single time? Vertically, however, the motion is a little more exciting. It starts out with a very large positive vertical velocity. And then, as it goes up, it's going to slow down. How quickly is it going to slow down? Well, technically, it's going to slow down 9.8 meters per second every second. That's the vertical acceleration, after all. So that'll be slower. And then slower. Now, highest point. Well, what's it doing at the highest point? Well, just before the highest point, it's going up. Just after the highest point, it's now going down. So it is changing direction at the highest point, and that means its velocity is 0. So highest point, no vertical velocity. Still accelerating, otherwise it wouldn't come back down, but its velocity vertically is instantaneously 0. However, on the way back down, now it's going to accelerate 9.8 meters per second faster every second and speed up on the way down. Now, before we draw this arrow here, though, think of the symmetry. Since it is going to speed up on the way down just as quickly as it's slowed down on the way up, the velocity right here should be exactly the same speed as the velocity here, just in the opposite direction. So this arrow is just as long as this one. Don't fill in the space between the dots. And this arrow should be the same length as this one. And this arrow should be the same length as that one, except it goes off the screen. So if you are filling in your worksheet, as you really should be, to complete your worksheet and to make it more of a motion map, you really ought to draw this arrow the same size as this. So notice here we can see again, constant velocity horizontally paired with uniformly accelerated motion vertically makes this nice parabolic shape of a two-dimensional projectile motion.